Okay, so today we're going to learn how to do the two sample t-tests using R. If you've been poking through my R code that I uploaded to the website, you may have already learned how to do some of this stuff. And we'll also learn how to do power for all the different t-tests using R. The homework example isn't that far-fetched, so you were supposed to pretend that you were a student and there was some psychology professor that needed help with their analyses. This actually happens sometimes. There are students who serve as statistical consultants, and they help sometimes professors. Most of the professors don't need help, but occasionally there are a couple that do. Also, in graduate school, people have to do dissertations, and often they have to do statistical analyses as part of their dissertations. And if they haven't paid as much attention in statistics, they need some help. So if you are good in statistics, you could potentially make some money and help out students doing statistics, or potentially even faculty members. Sometimes people will even set up websites, and they'll get people from all around the world asking them for their help. So you can make money with statistics. All right, so let's get into it. So if you don't already have the data, grab it. It's the data from the homework. EO. I think my battery might be dying. This might be a little awkward today. Does everyone have the data? All right. If you have the data loaded up, do this. Stir data. Okay, so when you do that, it says data frame. What else does it tell you? It tells you there's sample 1 and sample 2. So occasionally I might, for homework, say, okay, use this data. So you save the data, you load the data, but you don't know what the data are. And I say, okay, use the sample 1. Well, it might not be called sample 1, it might be called S1 or something else. So if you're not sure what you should use, you can look at stir data to try to figure out what I mean when I say use sample 1. Okay, let's assume that you've got the data loaded. Don't. Did it quickly. Let's make it easier to work with the data for you guys. Go ahead and assign sample 1 and sample 2 to variables that you can use easily. You guys have it back there? See that? Videos? Does it go? All right, well, while they are catching up, let's talk about doing t-tests the easy way. So the first question on the homework was something like, there's this professor, they designed this happiness scale with a mean of 100, and I don't think I said what the standard deviation was. If I did, you wouldn't have had to use a t-test, you could have used a z-test instead. So it has a mean of 100, and higher scores indicated happy people. And the teacher had this idea that people who use Facebook more frequently are less happy than people that use Facebook frequently. So this could translate into a one-tailed hypothesis. So the null hypothesis would be that the mean happiness of frequent Facebook users would be greater than or equal to 100, which is the mean of that happiness scale. And the alternative hypothesis would be that the mean of frequent Facebook users is less than 100. Okay, I said let's use an alpha of 0.01. So you had to go through, yeah?
Why did the hypothesis say more than 100?
The null hypothesis should be less than 100. Or, I'm sorry. Why the null hypothesis is more? Why did I say that the null hypothesis is more than 100? Equal to and more than. Greater than or equal to.
He wants to allow the W to use discover he's interested in whether non-frequent Facebook users are unhappy.
Yeah, so he's interested in whether or not frequent Facebook users are less happy than average, right? So if he is interested in determining whether frequent Facebook users are less happy, that's a one-tailed sort of interest. Does that make sense? So if you're interested in showing that Facebook users are less happy, then the null hypothesis should be that they are as happy as the mean or more happy. Does that make sense? Because the thing he's interested in is this, or she. Okay, yeah.
Can you open this slide?
Just assign the sample 1 and sample 2 data, the one before this. That. So you want homework 18. So if you go to homework, the last homework, you should be able to find a link to that and you should be able to go. Okay, so run this. So what?
The p-value of T.
Okay, what is it?
P-value 0.006.
0.006.
This is also 0.0.
So you should get something like this. So the p-value is 0.006.
Yes.
T is negative 2.6 something. Now notice the form that I used here. So t-test, I gave it the data that I'm going to be using to test, which was a sample 2. And now I said mu equals 100. Why?
Because our mean is different.
Yeah, this is what the null hypothesis gives us. If you don't specify mu equals 100, t-test will assume that you're looking for a mu equal to 0. But we're not looking for a mu equal to 0. We're looking for a mu or a mean equal to 100. So that's why we specify that here. Now the alternative, this is one of the parameters that t-test can take. So if you don't specify alternative, it will assume that you want to do a two-tailed test. But since we specify the alternative less, right? So the alternative is less than 100. Now, we didn't actually specify alpha anywhere in this line of code. We didn't have to.
Well,
If we wanted something, we would have to do it. Why didn't we need to specify alpha here?
we are not calculating critical.
We're not calculating the critical value, so by using t.test, we sort of jump over that step of calculating critical values, so we don't need to do it. All we need to do is look at the p-value, right? We compare our observed p with alpha, and what should we do?
Reject.
We should reject the null hypothesis, right? Why?
Because p-value less than.
Because p-value, this, is less than or equal to alpha.
Which p-value is it for which mean? For which observation? The p-value.
This p-value is for all of these data.
The mean of
It's the mean of the data, comparing the mean that you got here against this hypothesized mean with a one-tailed alternative hypothesis. Yes?
So when we said like alternative is less and equal, what will we do? For example, is it
Well, the alternative should never have the equal in it. The alternative should either be not equals, or less than, or greater than. It should never have equal in it. But go ahead. So if our alternative was what?
like less and equal, S and small,
As or small.
S or small.
Cannot be.
The alternative is never as.
Okay, that's okay.
Because your null hypothesis always includes the equal. Right? And we need that equal part to give a t-test something to calculate against. Right? We need some value to start our calculating our statistic. If it was just that the null hypothesis was greater than 100, well, we could use 120 or 150, but since it says equal to 100, that's the smallest that we think it should be, right? Okay. So now, what if you wanted to find the confidence interval? Is this the confidence interval for the alpha 0.01? No. What would you need to say to change this to if you wanted to use a 0.01 confidence interval?
Conf level.
Conf level equals,
Answer. No.
yeah, 99, exactly right, 1 minus alpha. Conf level 99. And if I asked you to give me the smallest confidence interval, what then should you do?
Alpha.
Yeah, you should get rid of this alternative. Or say two-tailed. I think that's a valid option, not positive. But yeah, so for the smallest confidence interval, you need to specify conf dot level and then use the two-tailed version of the test. Do you have a question? No. Okay. So we reject no. Awesome. Now, let's find power. I mentioned this before. I'm not going to show you the long way to calculate power because it would involve calculating a new distribution. Think about when we determined the t-distribution. What did we do? We said, originally when we calculated the t-distribution, what we did is we said, okay, imagine that we have two sets of data with the same mean and the same standard deviation. What would happen if we subtracted every score, every possible mean from every possible mean, right? We got something that was nice and centered on 0. Now, if we are predicting a difference that isn't 0, the t-distribution is centered on 0. So we would actually have to create two sets of data, one with a mean that is 2 larger than the other one, and then subtract all of those potential means from all the other potential means, and that would not give us the same thing as a t. It would be close to a t, but not the t. It would be the non-central t. We're not going to talk about that anymore. Instead, we're going to do it the easy way. We're going to use power.t.test. Now, like a t-test, power.t.test takes a lot of parameters. So let's go through some of the parameters that it takes. One is n, that's the sample size. Now, it's not the total sample size because sometimes we'll be using paired t-tests or independent t-tests where you might think you would add those things together. So instead, it's the sample size per sample. Okay? So if we had 2 samples with 36 observations in each, 36 would be our sample size, not 72. Okay, so it takes the sample size, it takes the difference between our observation and what's given by the null hypothesis. So previously, if we went back, we saw that the mean of x here was 93, and the hypothesis was 100. So it's going to be the difference between those two for the one sample test. It also takes SD, standard deviation. Now, this is the standard deviation that you would use when you were computing the standard error term that should go into calculating the t. So the standard deviation that you're going to use is going to be different for the different types of t-tests that you use. So the standard deviation for the one sample t-test is just the standard deviation based on the unbiased estimate of the sample. For the two sample independent t-test, the standard deviation is going to be the standard deviation calculated on the pooled estimate of the variance of those two samples. And then finally for the paired t-test, it's going to be the standard deviation based on the unbiased estimate of the variance of the differences. Okay. The significance level, it's just your alpha. Type. This is the type of test that you're going to be using. And in order to tell it what type you want, you can give it one of three types. One sample, just a regular old, plain old t-test. Or two sample, that's the independent version of the t-test. And then paired. It's two samples, but it's a paired two samples. So we would use paired for that. Finally, we can specify the alternative. Now, this is one thing that I'm not a huge fan of with the power.t test. You can't say like two-sided or less or greater. You can only say one-sided or two-sided. And because you can only say one-sided and you're not able to specify less or greater, you have to think when you are using power.t test if you're going to get the right answer. And we'll see an example of that in a little bit. Okay, so let's find the power for the test that we just ran, that one sample t-test. So n, this is just the size of that second sample, which we can calculate by using length, S2. Delta, this is the difference. So delta is, in Greek, typically is used in mathematics to symbolize the difference. So the delta is the mean that we observed in our sample, minus 100. If you think about the form of the t-test, we have something like this, right? So this part up here, this is our delta. The standard deviation, this is just the standard deviation based on unbiased estimate of variance, which is just the standard deviation of that sample. That's what we use when we compute this. It is not the standard error, but it's what we use to compute the standard error. Alpha is 0.01. Once you've got all that entered, go ahead and do power.t.test, all this junk. Power is almost zero.
It's zero.
We have like no power, you're saying.
No. Zero.
So if you do this, you should get an answer. Where is an answer like this. So power is 6.15 to e to the negative 7. That's very, very small. That's very close to zero. Is that right? You're shaking your head. That's not right.
I find different standard deviation and power.
You found a different standard deviation?
And power. That is
So what's the standard deviation that you found?
she wrong.
Huh. So have you guys got this?
Yeah.
Power is like close to zero? So the question is, okay, we can forget about her if she got the wrong answer. But
Okay, so
does this seem right?
it's a,
It's okay. Is this right?
I'm fine the same thing.
You're saying no. Why? Why do you say no?
I guess this is the other side of power, which should be just in this.
So this is beta, you're saying?
Yeah, so
significance level, this actually isn't the power that we're looking for. Let's draw our distribution. So I said that drawing your distributions helps, right? So we have our distribution, right? T, and we say that it's 100, right? Now, our null hypothesis says that it is greater than or equal to 100, which means that we're looking in this table, right? Now, we found some t-value, I forget what it was, but we found that the actual value was like 93 something. The mean that we computed was 93 something. So that was down here. And what did we do? We rejected the null hypothesis, right? Now, if we're going to find power, so we would create the non-central t-distribution centered on the 93 that we observed. And then we would have the critical value, whatever this critical value was, not of the t, but of the actual regular raw squares, which you can convert to and from using the formula. Anyway, so the critical value would be over here. Now, the power is basically the probability of correctly rejecting the null hypothesis. That is, rejecting the null hypothesis when it's false, right? So we would reject the null hypothesis anytime we see something at or below this. So we would want to sum up all of that. Now, we rejected the null hypothesis. So what does our power have to be? It has to be something.
It has to be less than the B or something.
Well, okay, power, if we are rejecting the null hypothesis, power has to be less than B or greater than B.
No, great.
If we're rejecting the null hypothesis, power should always be greater than B. At least when we have a one-tailed sample like this. So, if we reject the null hypothesis, we should know that power has to be greater than or equal to 0.5. Right? Because 0.5 should get us up to here. So, if we're rejecting, we want probably someplace beyond that. So it should be more than 0.5. So we got the wrong answer. Okay, so why did we get the wrong answer? It turns out that power.t-test is stupid for one-tailed hypotheses. It calculates power as if the user wanted a positive t-score or a positive d. So here we were looking for something that was negative, right? We were going to reject if we had a t-square that was negative and was far enough away from 0, right? So if it's calculating power as if the user wanted a positive t-score and we actually wanted a negative t-score, what should we do?
1 minus?
Not 1 minus, but it involves something with the 1 and also with the minus. No.
Minus 1.
Minus 1? What? You're on the right path. Minus 1 what?
I don't know.
Now, the distribution is symmetric. But what we actually ended up calculating here was something like, I'm going to get flipped around. Like the t that we observed was here, and we just want that tiny little bit over there. When actually it's flipped. I'll give you the answer. We'll see if it makes sense. So you need to be smart when you're using power.t.test for a one-sample test. If you're doing a two-sample test, it's no big deal. So what you do is you multiply delta by the sign of the t-squares in the alternative tail. So here, we were interested in this tail, in the less than tail, which would give us negative t-scores. The signs of those scores are negative. So we can multiply delta by negative 1, or by minus 1, and get the delta that we want to use. So go ahead and do this. So delta equals negative delta. That will flip the sign of the delta. you do that, just type delta and tell me what you get. Now it's 6.7. Before it was negative. So now, by giving it a positive value of the delta, we basically sort of flip what we're telling this that we're interested in, and we should be able to get the right value. So go ahead and do your power.t test with the new delta.
0.57.
0.57?
Yes. Yes.
5763.
It's bigger than
Sweet. That makes sense. Should be bigger than 0.5 for exactly the reasons that we said before. So if you are doing a power.t test and you get an answer, think about the answer that you see and think, does that make sense given my null hypothesis? Does that make sense given the decision that I made based on t-test? And because sometimes you might make a little mistake. And if you think about what the answer is and what you were expecting the answer to be, you can catch yourself. I'm guessing at some point this semester I will forget to make this stupid little minus delta change and the homework will end up wrong and whoever tells me about it first will get extra credit. Yeah.
Whenever we use this and change delta, that will give us the correct power.
For the one sample test. But we don't just blindly multiply delta by -1. We only multiply delta by -1 when we are expecting, when we're interested in getting a negative t. If we're expected in getting a positive t, just leave delta alone. Just use it as it is. But if your one-tailed hypothesis is looking for negative t's, then multiply delta by -1.
You said something about the hard way. When should we use the hard way, but we cannot use this way? The hard way.
When should you use the hard way? I'll mention when you should use the hard way in a minute. Okay? If you do the hard way, you should get exactly the same answer that you get with this way. Except in one situation, which we'll talk about in just a minute. Alright. That's much better. Okay, so our two-tailed test. Then I said, okay, so the teacher freaked out, and they said, why did you do a one-tailed test? Do a two-tailed test. You say, whatever, okay, you're wrong, but I'll do it anyway since you're paying me. So you do the two-tailed test. So, you can say t.test, give it the data, tell it the mean that you're expecting, but now your alternative isn't less or greater. Since t.test assumes you're doing a two-tailed, you don't have to specify alternative here, and you can get your answer just like that. So what is it?
0.1. 0.01. So we say
The p-value?
yes.
0.0128.
Yes.
Great. What should we do?
Fail.
Fail to reject. Why?
Because it's bigger than alpha.
Because 0.01 is bigger than, 0.012 is bigger than 0.01, right? So we should fail to reject. That's absolutely right. What if we wanted the smallest confidence interval? Do we have to do anything?
Yes, confidence level.
We'd have to specify confidence level. Now, since we didn't specify the confidence level, it spits out a confidence level, or the confidence interval, for a 95% confidence interval. So if we wanted the 99% confidence interval, we would need to say conf level equals 0.99, right? Okay, great.
0.99?
Yeah, 1 minus alpha. Okay, let's now move on to the next. Defining power for the test that we just did. So to find power, we need n. You guys should already have that. Delta, it's the same thing that we had before, so you have that. Standard deviation, it's the same thing you had before. So all we need to do is use power.t test, and what have I changed? The alternative before said one-sided. Now the alternative says two-sided. Groovy. Okay, so go ahead and do that.
We are using minus delta? No, we are not using.
Are you using minus delta?
No.
No, why not?
because it's for monthly.
We have a two-tailed hypothesis.
Okay.
We can test this. So someone said like 0.468, right?
Would it be the same?
Well, let's find out. I think on my next slide. Oh, I guess I didn't do it. Okay. Go ahead and do power t-test. Do the exact same thing, but put d equals minus delta.
The same, though, so.
Did you do it already? You get exactly the same answer.
Yeah.
So you only need to worry about delta when you're doing a one-sided test. Why? Because the t-distribution is symmetric. All right. Okay, so the next part for the homework said that the teacher came back and they freaked out because they forgot to give you half the data. So they gave you half the data and they told you to do an independent t-test where you subtract sample 2 from sample 1. And the hypothesis, the null hypothesis, is that the mean of infrequent Facebook users minus the mean of frequent Facebook users equals 0 if you're doing the two-tailed test, right? Okay, so go ahead, t.test, give it sample 1, sample 2. Now look what I said here, var equals true. Why did I do that?
Because sample size were the same, and so variance were the same.
It's actually not because of the sample sizes were the same. It's because for the independent t-test, what I said is that we should assume that the variances are the same and compute a pooled variance estimate, right? So in order to tell t.test to assume that the variances are the same, we need to say var equal. It means variance is the same. That's true. Okay? So what do you get?
0.178.
0.1786 for the p-value? Good. Now let's try something here. Because sometimes this assumption that the variances are equal is not warranted. So, if you take that out and say t-test, S1, S2, and that's it, what do you get?
A little bigger p-value.
You get a little bigger p-value. Okay, what else?
Interval are same.
Confidence interval's the same?
Yes.
Degrees of freedom is.
No, different.
You say it should be different. The degrees of freedom, what's the degrees of freedom?
Yes, right.
Well, so here the degrees of freedom was 72. What are the degrees of freedom when you...
69.
69. Point something, I'm guessing, right?
Yes.
So, if you want me to teach you how to do the t-test without the variances equal to true, we could do that, but you can learn about that in graduate school. On the homework or the test, I made something like, don't assume that the variances are true, in which case you wouldn't say var equals true. So you'll be able to get the right answer without knowing how on earth they calculated the degrees of freedom that they ended up calculating. Okay, so we should fail to reject the null, right? Because the p-value that we observed is much greater than alpha. Try this. So we just did t.test S1, S2. Do t.test S2, S1.
Same. Because it's not.
It's the same?
No.
Let's take a look. I'll put the
Minus 1.
yeah. So our t here, when we said S1, S2, was 1.35 stuff. When you change it, you get it minus 1.35. And notice also that the confidence interval flips as well. So with this version, we have negative 2.11 to 11 something. If you specify it the other way around, you should get negative 11 something to positive 2. So in the homework and on other slides, I've said something like always subtract the second from the first. so we get the same answer. So if you submit a homework or something and you get the wrong answer, try changing the sign, and then you might discover why you got it wrong if you specified things in a different order.
But
Okay.
is the same.
So what? P-value is exactly the same because the t-distribution is symmetric. So if you find something here, find something here, where it's centered on the same thing, you'll get the same p-value. At least for the two-sample, or the two-sided hypothesis. You get different ones for one-sided hypothesis. But for the two-sided hypothesis, you'll get exactly the same p-values, but your t-values will be different, and so will the confidence intervals. So your answer depends on the order in which you specify the data when you're using two samples, so be careful. Okay, let's find the power. Now, before we said that we had to specify n, here I've said n equals length 1, or n1 equals length of S1, and 2 equals length of S2. Now, for the homework example, these were exactly the same, right? Which is why you were able to do a paired t-test. If you didn't have equal sample sizes, like you couldn't subtract, there's nothing from something. But if you have unequal sample sizes, in order to use the more appropriate n, you should take the mean of the different, or the minimum of the two different n's for the different sample sizes. This is where doing power the hard way is going to be better. Because by doing power the hard way, you can account for the differences in the sample sizes. Whereas here, you're only giving it one sample size. So this answer, when you have different sample sizes, will be different than what you would get calculating power the hard way. Why do we use the minimum of the sample sizes? Why don't we use the maximum of the sample sizes?
Because if we use maximum, some values couldn't be matched some.
But even if we use the minimum, that value isn't matching everything, right? Think about the standard error term. The standard error term, we are dividing by sample size, right?
If sample size is smaller, our t will be standard deviation, SAM will be more.
Yeah, if the sample size is smaller, the standard error will be bigger. Now, if you want to calculate power, if you calculate power using the larger sample size, you are going to overestimate your power. If you use power using the smaller sample size, you will end up underestimating your power. What's better to do, overestimate or underestimate? Underestimate, why?
You guarantee.
If you are underestimating, you know you have at least this much, right? Okay. So we'll use the smallest of the two sample sizes if we're doing an independent t-test and we have different sample sizes. If we have the same sample sizes, it's really easy. We just use one of them and we're fine. Okay. Delta. So we have our independent t-test, and the formula for t for our independent t-test is mean 1 minus mean 2 minus mu1 minus mu2, like that, right? All over the standard error, right?
Yeah.
And we said when this hypothesized difference is 0, well, that just drops out. And we have something like this. So our delta is just the first mean minus the second mean. Don't even need to worry about that there. But I put it in anyway, so if we are predicting a specific difference, you guys know how to do it. Okay? All right, so there's our delta, our standard deviation. Which form of the standard deviation is this?
Cool, baby.
Yeah, this is based on the pooled variance. So in the middle we have our degrees of freedom for 1 times the variance of our sample 1 plus degrees of freedom 2 times the variance of our second sample, that's 2, all over degrees of freedom 1 plus degrees of freedom 2 minus 2. Or I'm sorry, all over our degrees of freedom 1 plus our degrees of freedom 2, which is n1 plus n2 minus 2. All right. Alpha, we've got the same alpha. Did everyone have that? You guys need another minute to finish that? Good? Ooh! Whoa, what happened? What happened? Aha, good. Okay. So go ahead and use the power.t test. Your power.t test. Notice what's changed here?
2 samples.
Our type. Instead of 1 sample, it's now 2 samples. Everything else is the same, so you can just up and change 1 sample to 2 sample and you should be good to go.
1, 0.1.
This?
Yes.
So the p-value is 0.1, oh, I'm sorry, the power is 0.1059. Groovy. All right. So, the last part of the homework was that the teacher came running back and said, wait. These are paired data. They're dependent data. You're right, they should have been correlated. So, we now have a new paired t-test. What's the difference between this and the previous?
Paired.
Paired equals true. What if we wanted to do a one-tailed, less than hypothesis? Comma, alternative equals
Less.
less. Great. All right. So t.test that, what is it?
0.001.
So the p-value is 0.001726.
Reject.
We reject. Why do we reject?
P-value less than.
Because 0.001 is less than 0.01. So reject the null hypothesis. Beautiful. Again, if you wanted to do the 95% confidence interval or a 99% confidence interval, you need to say conf dot level equals whatever you want. Okay, try this. So do exactly the same thing as before, but use S2, S1 instead of S1, S2. Negative. What's negative? T is negative, and also the mean is negative. And what else? The confidence level also. Great. Okay. So let's apply the power. N, we can use the same N that we've been using. Delta now. This is going to be mean S1 minus mean S2 minus 0. That's the same delta that we used before for our independent test. And now our standard deviation is different. It's not that pooled estimate. What is it? It's the standard deviation of the differences. All right, Ruben. So go ahead and find the power. What's the difference here? Type now is paired instead of 2 sample or 1 sample.
Power is
0.74.
Yes.
Does this make sense? We rejected the null hypothesis. It should be big, right? Should be bigger than 0.05. All right, one more example. This was not on the homework. So imagine that a happiness score of like a 95 meant that the person was depressed. So like 100, you're okay. 99, you're okay. 98, 97, 96, you're okay. But a 95 is an indicator of depression, right? Now, if Facebook users are just a little bit less happy than Facebook users, maybe that's, than non-Facebook users, maybe that's not a big deal, right? But if it pushes them so far away that now the Facebook users are basically depressed, so 95, if 95 equals depressed, that might be something that's really important, okay? So imagine then you could change your null hypothesis. So the mean of non-Facebook, no Facebook, minus the mean of Facebook equals 5. Or, since this is a one-tailed thing, I said we're interested in 95 or lower, you want to determine if they're depressed. So if this difference is greater than or equal to 5, right? Restated, that is this. So the alternative hypothesis would be that the mean difference is greater than 5, right? So their scores are below 95, but the true mean really is on. Do you have a question? All right. So go ahead and do this. What's difference? Or what's different than before? Not the p-value.
Big equal to.
So we had paired equal true the last time.
Just one thing.
It's just one tail now, right? Notice this is greater, so we specify greater there. There's one other thing.
T-test, not for.
This. Right? Previously, if we go back, we didn't say mu equals anything. Why? Because when we don't specify mu, t.test assumes that mu, or the mean, the expected thing that you're looking for, you're not looking for, the expected thing under the null is 0. So here we said that the difference is not expected to be 0, that the expected difference is expected to be 5, right? So we indicate that here with mu. And when we calculate it, p-value is 0.6397. Now you might say, okay, does this p-value make sense? Does this p-value make sense? How do you tell? Draw the distribution, right? So here, if the difference really is 5, and we are interested in something greater than 5, we're interested in something over here, right? So things like 6, 7, 8, 9, 10, those are greater than 5. But what did we observe? What was our mean difference?
Or going to point something.
So what we observed was something over here, right? 4.5. Now the p-value is the probability of observing something that or more extreme. And we determine what's extreme by the direction of the test, right? We have a one-sided test. So stuff over on this side is not extreme. Stuff on this side is considered extreme. So things that are more extreme than 4.5 is 4.6, 4.7, 4.8, 4.9, 5, all of this. This part here should be just this part.
0.5.
0.5, right? But we're on this side, so it should be greater than 0.5, right? And was it? Yeah, 0.6397. Okay, that p-value does make some sense. Okay, what do we do?
Fail.
Should fail to reject. DOD. All right, let's find the power. So we already have the n, we already have the standard deviation that we computed last time, we already have the alpha. The delta here is different though, right? So the delta, again, if we draw our formula for the t, we got the standard error on the bottom, x1 minus x2 minus mu1 minus mu2. So this part in here, this is 5. So we should take the mean of sample 1 minus the mean of sample 2 minus 5. Okay? So what do you get?
Very little power.
Huh?
Very small power.
Very little power, right? So 0.00375,
No.
1,
0.01,
0.239.
0.0329.
2, 3.
What did you get?
Are these the same?
You got the same as this, 0.0037? So retype this, make sure that you've got the same thing. You have one-sided?
Yeah.
Yeah, thanks for noticing that. Did you get 0.0037 yet? You got it? We shouldn't have much power.
Okay.
If our rejection area was right here, according to the null hypothesis, if we redrew this like that, before we had 0.01 over here, right? But now, since we have shifted things, we should have even less than what we had before, less than 0.01, and we do. 0.0037. That makes sense. Ruby? All right. One more cool thing that we're going to talk about today. That's a priori power. Okay, so back when we first started talking about power, we said that we can compute power in 2 different ways. We said that we can compute it after we did our test to see how much power we had to observe what we actually observed, right? And that was posterior power, right? But we said that we could also calculate power before we ever do anything. Now, the way that power.t-test is set up, you specify a lot of parameters, right? We've been specifying n, we've been specifying the standard deviation, we've been specifying delta. Well, the cool thing with power.t-test is you can specify the power instead of specifying n. Or actually, you could specify the power and n and leave out d. You can leave out one of these crucial pieces to calculating power and specify the power that you want instead and see what alpha level you need to use or how large your sample size needs to be. So let's say you were going to do an experiment using t-tests and you wanted to know how many people that you needed to be in your samples. So here I said we want to know how many participants you needed to detect the difference between the means of 10 when 0 is expected and the standard deviation is 10. You want to use a one-tailed alpha of 0.01. You have a power of 0.8 and plan on using a paired design. So I've given you enough information to specify a power.t-test. I've given you everything basically except for the n, right? So I say power t-test, power equals 0.8, d equals 10, right? If we specified 5 was expected, then we would have 10 minus 5. Just that upper part. Okay, so D is 10. Standard deviation is 10. Significance level, 0.01. You want to use paired. Did I say something about the alternative?
One tail off. Yes, one tail off.
One tail off. Okay. All right. Ruby, so do it.
11 points, 12 points, 12 for N.
12 point something. So that means you need 12.866 observations for each sample. Does anyone have a problem with that?
You cannot.
You can't have 0.866 of an observation, right? You can have 12 observations, or you can have 13 observations. So before we talked about what we should use the smaller or the larger, and we want to be conservative, right? So if we want to make sure that we have a power of 0.8, should we use 12 or should we use 13? We should use 13. So if I ask you, how large should your sample be on homework or on a test, don't give me this. Unless it says 12.00000. Okay, then use 12. Otherwise, round up. Because you can't have a part of a person. Unless maybe you're like watching Saw or Hostel or some of those horror movies or something. Whatever. Okay. What if you did a two-tailed test instead of a one-tailed test? Everything is exactly the same except my alternative. Before it said one-sided, now it says two-sided.
15 points again.
So how many people should we use?
16.
Use 16.
No, it's 15.
15.
No.
Because it's 15.08. So it's O first, not
But what did I say? I didn't say round. I said round up.
only round up.
Only round up. Because you can't have 0.05 of a person. Right? What's 0.05 of a person? There? Always round up. Okay? Because if you use 15 people, you won't have 0.8 power. In fact, you can check this. So why don't you get rid of power, so do exactly the same thing and say n equals 15 instead of power equals 0.8.
So it's just like
It's lessening, and we want 0.8 for our power. We want at least that much power. So what do we use? 16. If you change n equals 16, you should get something now greater than 0.8. Okay. What if you use now 0.05? What do we need to change? Sig level, or significance level. Instead of 0.01, now it's 0.05. 10. What if we did an independent test? What do we change? Instead of paired, now we use two sample. 17. Why? Because that variance should be larger on the bottom, right? Okay. What if we use a larger standard deviation? Well, the standard deviation was 20. Well, we can change SD from 10 to 20. A lot. 64. So this is how a lot of people use power to figure out how big of a sample size they need, or how big of samples they need if they want to have a certain amount of power, if they are expecting a particular difference, and if they are expecting a particular standard deviation. So how can you figure out what the particular difference might be? You look in the literature. What have other people found? What standard deviations have other people found? And then design your experiment so that way you have sufficient power to be able to detect an effect when it's there. Now you won't always, right? Because what's beta if our power is 0.8?
0.2.
0.2. So we'd still be incorrectly failing to reject the null 20% of the time when we set it up like this. But we can give it the power that we want to have. Now, be careful. When you are performing two sample tests, make sure that you perform them in the correct order. So t-test S1, S2 does not equal the same thing as S2, S1. The signs of the t's flip, the signs of the mean flips, the size of the confidence intervals, those signs also flip. Be careful, use the right standard deviation for power. For the one sample, just use the standard deviation of that sample. For independent samples, you need to use the pooled variance estimate to determine your standard deviation. For paired samples, you want the standard deviation of the differences. You need to use the right n for power. For one sample designs, you just use the size of the sample. For independent designs, if you have different sample sizes, you want to choose the smaller of those sample sizes, so you aren't overestimating your power. For the paired, your sample sizes should be equal, so you can use the size of either one of those. You should also be careful and use the right D for power with one-tailed hypotheses. So you want to multiply the observed difference in means by the sign of the tail that's specified in the alternative. This is what we did earlier. When we were expecting a negative t-value to reject, we needed to multiply our delta by -1 if we wanted power to give us the right answer. And we multiplied by -1. We didn't subtract what we got from 1. If you remember that first example, the power, when computed incorrectly, was really, really small. It was like 0. If you subtracted from 1, it would be like 99, very close to 1, right? But we saw that the power wasn't close to 1. It was like 0.63 or something like that. So subtracting from 1 is not the same as multiplying by 1. All right, next lab, we will do ANOVA. That's it. If you have questions, want to go through extra examples, you can stick around. Otherwise, have an awesome weekend.